Good afternoon, guys.
Good afternoon.
I hope everyone is doing great. We're only 13 so far. Can you guys try to mobilize your friends to join the meeting? The sooner we begin, the sooner we finish. Okay, I don't know how many exactly are supposed to be doing mechanics, but for more than 20, I guess it's safe for us to begin. First of all, well, this is not an order, it's rather a recommendation. I'd recommend you guys use your actual names on Zoom because I would like to take note of who's having problems, who's asking questions, so I can know how to follow up. But if you have a name like Sucrose Daddy, Tambafie, Celine John, CK, I won't know who's asking what and who's lacking where. So it's better you just use your actual name. And as I said, it's not an order. So if you would rather continue with the nicknames you've put here, you are free to continue doing so, but you will be missing out on some special help or extra help. Okay, guess we can get right into the business of the day. So today we'll be introducing this module, Mécanique du point. As I told you last time in the briefing we had, it's the same physics you've been doing in Zambia, the same stuff. The notation might seem different and maybe there might be some differences here and there, but it's just the same stuff you are doing in Zambia. the velocity, acceleration, the vectors, it's the same things. So don't be frightened, don't be scared by the stuff you'll be seeing. Just remember it's the same things you guys were doing. And for mechanics, just a bit of advice. Mechanics has a lot of calculus and trigonometry, a lot of it. These two are like the backbone of mechanics. You'll be differentiating and integrating a lot, and you'll also be using trigonometric functions and operations a lot. So if you've never done these two topics, I recommend that you put aside some time to learn these two, not just for the summer lessons, but even for the lessons at school. Because most people have problems in mechanics, not because of the vectors or whatsoever we'll be doing in mechanics, but because of the mathematics in mechanics, the trigonometry and the calculus. So I'd recommend you do these topics. If it's been a while since you last did them and you are not sure, if you remember the stuff, you can at least go through also just to remind yourself of the stuff you did. But these two very important in mechanics, trigonometry and calculus. I hope we are taking note. So the introduction here, I'm sure you guys read through, it's just French, so I'm sure you understood. But what they're telling you here is physics in general, is interested by the things that surrounds it. And physicists, their primary goal, or what they want so much, is to try and understand why things behind them or why things around them happen the way they happen, why things interact the way they interact. They want to study these interactions. They want to make equations for these interactions. They want to characterize these interactions. And there's a lot of interactions that happen around us, an infinity of interactions. And so you cannot study them as interactions in general. So what physicists or scientists have done is they have broken down these interactions into smaller groups, okay? That's where you find fields like electricity, fields like the thermic part, the chemie, the chemical part, and also the mechanic part. This was just to make the study of these interactions around us very, very easy. Then the last statement here is saying, il ne faut pas oublier que ces séparations sont artificielles et que tous les phénomènes, toutes les interactions existent en même temps dans la nature. The electricity, the chemie, the thermal parts, not like they're happening differently. They happen at the same time, but they were just separated, they were just grouped to make their study very easy. But the separation is not a natural separation, no. It's an artificial one just made by us human beings. En séparant l'étude du monde qui nous entoure en différentes disciplines, nous en avons simplifié l'étude, mais même ainsi, nous ne pouvons mettre en équation de manière parfaite le monde qui nous entoure. Nous allons donc être amenés à faire des hypothèses sur le système étudié et à limiter notre étude dans l'espace et dans le temps. So this is going to be our basis in mechanics. We'll be studying these interactions in space and in time, but mostly in space, with time also here. Then the introduction here now goes on to tell you the objective of mechanics. These are just introductions. Okay, they're also interesting, but it's not really the nitty-gritty of mechanics or what we're going to do today. So they're telling you the objective is to try and describe and explain movement. So any sort of movement that you know, how cars are able to displace themselves from robots to start, or how a footballer sprints from one side of the goal or one side of the pitch to the other side, how a satellite is launched into space, how, I don't know what, any movement you can think of. So they're saying, so d'un athlète, accélération d'une voiture, lancement d'une fusée, trajectoire d'un proton, écoulement d'une rivière, all these movements and so many other movements that you can think of. That's the primary objective of mechanics. It is to study those movements, the translations, the rotations, whatsoever movement you know of. We are going to study them in mechanics. Et dans le cadre de ce cours, Nous allons nous intéresser uniquement aux relations mécaniques entre des points matériels. Now, this is mécanique du point. Later on, I'm sure you're going to do mécanique des solides. There in the solid now, you'll be studying solids. But here we are doing mécanique du point. So we are going to study the mechanical relations of these points, point matériel. Now, when they say point matériel, what do they mean? A point matériel is a point that is infinitely small, a very, very small point, like a dot, very, very small. There's a definition down here. I think you guys must have seen it when you are revising. They defined it. They said infiniment petit. C'est un point qui est infiniment petit. That's a point matériel. And then there's a part here, somewhere here, where they explain. They say, when we say infiniment petit or infinitely small, we do not mean necessarily that the point has to be small, like a dot or like a proton or an electron or whatsoever. No, sometimes the smallness of this point depends on the observer. I'll give you an example of a satellite in space. If I am observing a satellite in space from here on Earth, how is the satellite going to appear to me? It's going to be very small, not so, because I, as an observer, I am very far from it. So the observation of the movement of that satellite in space is going to go under mécanique du point, because the satellite then has become a point matériel because of the position of the observer, because of the distance between that satellite and the observer. That satellite has become small. Even if the satellite is a solid in itself, it's got big dimensions, but its dimensions are very, very small. They are negligible when compared to the distance of the observer from that satellite. I don't know if that's clear. Is it clear?
Oui.
Kindly repeat.
Okay, I'm going to repeat. And I want you guys to be stopping me whenever I say something that's not clear. I don't want anyone to remain behind. Let's move together. That's why we're here. So where should I repeat from? Where should I start from repeating?
Just start afresh. So it take you behind.
From the very beginning of the introduction.
Yeah.
Okay, so I was saying in the introduction here, they're telling us that physics is concerned primarily with the world around it or around us. And physicists have tried to study, to make equations about the interactions that happen around us. Okay, there's literally billions, there's an infinity of interactions around us. And what we're trying to do as physicists, like us today now, we are trying to study these interactions. Okay, you have fields like electricity. You are studying the interactions of electrons. You get mechanics, you get thermodynamics, all these fields. You find physicists trying to study the interactions around us. And there's a lot of them, as I said. And because there's a lot of interactions around us, it's very difficult. Yeah, it becomes very tricky to understand or to study these interactions in general. So what physicists did was that they grouped these interactions into smaller subgroups, okay, into different fields. That's why you have fields like electricity, you have fields like chemistry, you have fields like a thermal field, the thermodynamics, and you also have mechanics. This separation was just done to make the study of the interactions around us easier. Imagine trying to study electricity and mechanics as one, or trying to study chemistry and thermodynamics as one. It would have been kind of complicated to understand. But you isolate electricity and you study electricity profoundly on its own, you find that the work becomes easier. You isolate mechanics and you try to study mechanics on its own, and you find that the work becomes even easier again. So that's why they were broken down into these subgroups. And then the reminder said, don't forget that this separation is not a natural separation. It's not like when the world was created, there was this field of electricity this side, there was the field of chemistry this side, or thermodynamics this side, or mechanics this side. No, it was just an artificial separation done by human beings, as I mentioned, to make their work easier. And after we separated these fields and studied them intensively as physicists, we have come to learn a lot about these fields. And also, as we are going to study mechanics today, we are going to use some hypotheses, as they are saying here. Nous allons donc être amenés à faire des hypothèses sur le système étudié et à limiter notre étude dans l'espace et dans le temps. As I mentioned earlier again, mechanics, we are studying the movement of objects. We are trying to explain, we are trying to describe the movement of objects. Now, what are we using to explain these movements? We are using, first of all, space, because for something to move from one place to another, it has to do it in space. And we also have to take note of the time it's taking to do all these movements it's doing. That's why they are saying we are going to limit our study in space and in time. And then I said, in our cours that are going to follow from now on, in Mécanique du point, as the name itself suggests, Mécanique du point, we are going to be studying the movement of a point. Okay, so to say, a point, un point matériel in French is what they call it, point matériel. Now, what's a point matériel? It's a point that is infinitely small. In French, on dit infiniment petit, infinitely small, a very small point. You'll be studying the movement of that point, not like I, Charles, trying to run from my apartment to the nearby store, and you're saying Mécanique du point is going to help me explain the movement explain my movement. No, because I am not a point material. I am not infinitely small. I have big dimensions. Now, there's something to take note of here. I'm sorry, this is where some of you got confused. It is that when we say un point matériel and we say its dimensions are very small, it doesn't necessarily mean that the object we are studying is very, very small, like maybe the size of an electron or the size of a proton or the size of a full stop. So you say un point, it's the size of a full stop. No, it's not always like that. It depends on the observer also. That is why I gave the example of a satellite. Let's say we are here in class as a Mécanique du point class. We are trying to study the movement of a satellite around the Earth. We are here on Earth. We are trying to study the movement of a satellite in space around the Earth. Now, what's the distance between us as observers here and the satellite in space? There's, I don't know if it's 1,000 or millions of kilometers in between. So when we look at the satellite from where we are here, the satellite is going to seem very, very small. It's just a point in space, okay? Because the observer is very far. So that means the study of that satellite also is going to fall under this field of Mécanique du point, because that satellite, its dimensions are infinitely small, or its dimensions are negligible compared to the distance between the observer and the satellite itself. So the point material, it can be a point or it can be an object that's very, very small with dimensions that are very, very small, or it can be also an object that is very far from the observer, making the object seem small from the observer's perspective. I don't know if that's clear.
It's clear.
It's clear for everyone?
Yeah, it's clear.
Okay. So, relation mécanique. What's a relation mécanique? Et c'est parmi les interactions physiques entre objets ou éléments, les relations mécaniques sont celles qui modifient l'état de repos ou de mouvement d'un système matériel ou de certaines de ses parties. Something that just makes an object act or move or something that changes its state of rest or maybe changes its state of movement. Those are the relations mécaniques dont on parle ici. Then we are going to go through some of the hypotheses that we are going to use in classic mechanics, what we'll be doing. En mécanique classique, nous allons étudier des systèmes matériels qui existent pendant un intervalle donné de temps dans un espace réel à 3 dimensions. Dans le cadre de ce cours, nous ne nous intéressons qu'au point matériel. So take note of this. In this school, we are only dealing with the point matériel and nothing else, not solids, not what, just the point matériel that I am from explaining. Then, la masse d'un point matériel ne dépend que de la qualité, de la quantité plutôt de matière qui le compose. Même si le point matériel est de dimension nulle, il est doté d'une masse. I'm sure that's clear there. They're saying even the points that we'll be studying, they have masses. When you go into chapter 2 of Mécanique du point, when we'll be doing the dynamic du point matériel, we are going to bring in now the concept of mass. And they're going to say, but that's a point, it's infinitely small. How does it have a mass? Yes, even if it's got 0 dimensions, it still has a mass. And as I mentioned, sometimes it just depends on the distance of the observer from the actual object we are studying. So the object might be big in nature and might have a mass, but we're going to treat it as a point because of how far it is from the observer. So let's take note of this. They have a mass also, these points that we are going to be studying. Then finally, they're saying, on ne retiendra dans l'ensemble des relations entre le système et le monde extérieur que celles qui modifient l'état de repos ou de mouvement du système ou de certaines de ses parties. We already looked at this. Then finally, the last part of the introduction, then we get into some mathematical stuff. Limit de la mécanique classique. Now, where does the classical mechanics fall short? What doesn't it include? Number one, la mécanique telle que nous l'avons définie ne permet pas d'expliquer et de prévoir le mouvement de très petits systèmes matériels, typiquement les éléments constitutifs de la matière, voire de certaines particules fines, autres de grandeur de nanomètres or micrometer rather. So even though we are dealing with small points that are infinitely small, there's still a limit to how small they can be. Below the micrometer, we cannot study those points using classical mechanics. Now we have to bring in other fields of physics to study them. So below this limit they have given us here, the micrometer, we cannot advance the micrometer. De même, les mouvements des galaxies ne sont pas parfaitement pris en compte par la mécanique classique, galaxies. And finally, here, si la vitesse d'un système est proche de celle de la lumière, de nouveau, la mécanique classique ne s'applique plus. On doit utiliser la relativité. Now, I'm sure most of you love science and you've heard of the great man Einstein and all who formulated the theory of relativity. And I'm sure some of us are already aware that there are certain things that we can explain, that we cannot explain using mechanics. You know, some particles moving as fast as light or close to the speed of light. We cannot use mechanics to explain the movement of those objects. We now have to bring in the work of this great man, Einstein. That's what Einstein dealt with. Objects that move as fast as light or close to the speed of light. So when we are in that field, we leave mechanics and we are now dealing with relativity, which is not what we are doing today. So we won't get into details there. Okay, so I don't know if there are questions from the introduction of mechanics. I don't know if I've given you a good scope of what we'll be looking at of what mechanics is about. If there's questions from the introduction, please feel free to ask before we get into the next part of our lesson today. Are there questions? Okay, we'll take silence as a no. You guys are following, huh?
Yes, we're following.
Okay. I was worried. I thought I was talking to myself. There's 7 messages in the chat. Sorry, I wasn't checking the chat.
I lost connection. Can you kindly explain the last part?
Okay, the last part, the limits.
Wait, can you scroll down?
This is the last part.
Okay.
So I explained the limits.
Yeah.
Okay, so I was saying, okay, I didn't say this before. As beautiful and as interesting as mechanics is, it cannot be used to explain all the movements that happen on Earth or around us. Even though the primary objective of mechanics is to study movements, it also has its limits rather, much like anything else on this planet. So here are the limits of mechanics. Number one, la mécanique telle que nous l'avons définie ne permet pas d'expliquer et de prévoir le mouvement de très petits systèmes matériels. That means, sorry, I know I said we are going to study the points matériels. And le point matériel, ce sont des points qui sont infiniment petits. That means it can be very, very small, but there's also a limit to how small that point can be in mechanics. And they have given us an order here that the limit has to be the micrometer. Anything that's smaller than the micrometer, when you go into the ranges of the nanometer and whatsoever is below that, you cannot choose mechanics to explain. If you can just mute your mic. Yeah, you cannot choose mechanics to explain the movement of those objects because they are too small. Their dimensions, their sizes, their magnitudes are too small for mechanics to apply. The next one is the movement, the galaxy, the movements of galaxies in space. We cannot choose mechanics to properly explain their movement. And lastly, it's objects that are very, very fast. It's unimaginable speeds, the speed of light. Objects that are even close to the speed of light, or objects that move as fast as light. We cannot use mechanics to explain the movements of those objects. There now we are in the field of relativity. We use relativity to study, to describe, and to explain the movements of those objects because they are too fast for mechanics to apply. I don't know if that's clear.
C'est clair.
Ok, très bien, très bien. Now we do un rappel. I don't know how many of you did vectors in high school. Those of you that did additional mathematics must have done vectors. I don't know if vectors have now been included in the ordinary mathematics syllabus, but nonetheless, we are still going to look at them. Now, vectors are important in mechanics and in other scientific fields because things like vitesse, or let's not choose the word things, we can say le grandeur, like vitesse, acceleration, and force, they can be represented using vectors. And when you represent them as vectors, they are much easier to study. That's why vectors have a very, very important role and a very significant position in mechanics, in thermodynamics, or whatsoever field, even in electromagnetism. Yesterday, you guys were doing vectors. Yeah, they are very, very important because such things can be represented using vectors, and representing such things as vitesse, acceleration, and force using vectors makes their calculation or their study or explaining them quite easy, as you see when we shall be doing it here in mechanics. So it's very important for us to do a bit of a recap on vectors, to look back on them just to refresh our memories a bit. And again, if you have never done vectors in your life, that's another topic I hope you're writing down. So I've listed 3 things so far. So if you've never done vectors in your life, I'm going to try and explain today, but just try and do some extra work on your own, just to make sure you have an idea, you are stable in vectors, because these are important. Mechanics hangs on these from now on up until the exam or the control that you have at your universities next semester. You'll be doing vectors through and through in mechanics. Okay. On appelle grandeur physique toute propriété variable, ce qui peut être augmenté ou diminué. So we know what variable means. So a grandeur physique is anything that's variable, something that can be increased or decreased, que l'on peut caractériser par un nombre une fois l'unité de mesure est choisie. For example, you have a grandeur physique like la masse. the mass can be increased, mass can be reduced, and mass can also give a number. Let's say I weigh 60 kg. You know that we have to characterize that mass 60. L'unité de mesure est choisie. I'm sure we all know what unit de mesure is. The units of measure like the kilogram, degree Celsius, kilometer, the meter, and whatsoever units we have. So that's the grandeur of physics. I'm sure you guys have seen this. This was like the introduction of physics in high school. Deux grandeurs sont importantes en physique. Le grandeur scalaire et le grandeur vectorielle. We have scalar quantities and vector quantities. Sure, we remember this from high school, or we have an idea. So there's a definition of scalar quantity there, the grandeur scalaire. Un scalaire est une grandeur ordinaire déterminée par une simple valeur numérique, positive ou négative. Exemple, température, pression, charge électrique. In high school, we defined as a scalar quantity is a quantity that has what? That has no direction also. It only has size. It's the same thing they're trying to say here. That size is characterized by numbers, what they're saying qui est déterminé par une simple valeur numérique. So if I say I weigh 60 kg, that mass there can only be represented by that number 60 kg. That's all. That's all you can characterize that mass by une simple valeur numérique, because it's a scalar quantity. Vector quantities, on the other hand, have other properties that you have to consider. And they're saying here, pour définir certaines grandeurs physiques, un seul nombre ne suffit plus. It's not like the mass where you just say 60 kg and you forget, and someone is going to understand what you're talking about. When you're dealing with vectors, when I ask you what's the acceleration and you just tell me 50 kilometers per second, or sorry, the velocity, and you just say 50 kilometers per second, I'm not going to understand that properly, because in that case, we'll be dealing with vectors. I'll need to know the direction in which it's going. I'll need to know what and what, where it started from, where it ended from. Because when you're dealing with vectors, it's not all about the size. There's other factors, there's other properties that you have to bring in. And these properties are 4 in number. Number 1, you have the origin. For a vector, you have to know the origin, le point d'application rather. So we have this vector here, the vector AB, and we know that A, in this case, is the origin, le point d'application. So a vector should have an origin. Number 2, in direction. The direction is given by the line, this line here is saying la droite delta. So mostly when you have this delta here, it represents a line. So the direction is given by this line, the delta, and it's AB. That's the direction. Then it also has un sens. Un sens est indiqué. It's indicated by the flash, the arrow. The arrow is going to tell you the sens of the vector. Then you have the module. The module, this is what the two quantities, the scalar quantities and the vector quantities have in common. Both have modules. Even the vector, they have a module. The module is the size, the magnitude, okay? It's la longueur du segment AB. That's the size of this vector. So the vector has 4 properties, primary properties: une origine, une direction, un sens, et un module. Then we are going to distinguish 3 types of vectors. Okay, we have vector libre. I don't know if in English it's a direct free vector. I did not take time to look at what it's called in English, but in French, c'est un vecteur libre. C'est un vecteur d'origine arbitraire. So the vector libre, the origin can be anywhere. It's not just like A here have an origin. The origin can be anywhere. So this vector can be here, it can be put there, it can be put where, it can be put there. That's a vector libre. A vector, yeah. L'origine, direction, sens, et module fixe. That means all 4 properties, vector lié, they have to be fixed. The origin has to be fixed. If you say it's a vector lié, the origin,
Excuse me, can you kindly slow down?
Okay, sorry, I'm going too fast. So the vector lié, for vector lié, all four properties are fixed. They are fixed, they do not change. If you have a vector lié, the origin is fixed. If this vector is at point O, if it's a vector lié, it's always going to start from point O. It's fixed. Its direction is never going to change. It's always, if it's going north, it's always going to go northeast. Its sons, if the arrow is showing that it's going in the direction to the left, it's never going to change. It's going to be like that. And its size is also not going to change. That's why the vector lié is. All four properties are fixed. When we say fixed, it means they do not change. The opposite of fixed in physics is variable. When you say variable, it means it's changing. It can be increased or reduced. But for a vector lié, these four properties are all fixed. Then you have a vector glissant. For a vector glissant, it has three of its properties fixed. The direction,
Sorry,
and the
take you back.
module.
Can you please
Uh-huh.
explain on the vector libre again?
Yeah, vector libre. The vector libre, its origin is arbitrary. It means you can pick origin for the vector. Origin is arbitrary, so you get this vector. Maybe you can bring it here, you can represent it there, you can represent it there. It's libre. It's free to move in space. The difference between the vector libre is confusing, a bit similar to a vector glissant. The difference between a vector libre and the vector glissant is that, okay, both of them don't have fixed origins, but the difference is what we call the surport, what's supporting the vector. In this case, what's supporting the vector is this line here, delta. You've seen the vector going from A to B, but there's this thing that's exceeding this, and that's exceeding this. That's what we call the surport. For the vector glissant, the surport is fixed. That means the vector can only move on this line. The origin can only change on this line. So A can be here, or A can come there and B move there. That's the vector glissant. It's just like sliding. To glisse is to slide. Glisse, when you say glisser, it's to slide. So it's just like sliding on this line. Its movement is just limited to this line. But for a vector libre, the surport is not fixed. That means it can move from this line. It can come down here and move there. It can come down there and move there. It's free to move in space. You get it?
Yes.
Okay, that's great. There's the other guy that asked, have you also understood?
Yeah. Clear.
Okay, wonderful. Then we come to much easier stuff. We have some particular vectors of special nature. On the vector null, the null vector. It's a vector whose module is equal to 0, as the name implies, vector null. Then we have vector constant. It means its module is, or its magnitude is constant. It cannot change. So vector constant, module constant, the direction, essence fixe. So if it's going, if its size is 50, going in the direction northeast, it's going to keep on going in that direction northeast, and its size is going to stay there, or the size is going to stay the same. Okay, vector lib, is it one point which is known as the origin? For a vector lib, doesn't have one origin. Yeah, we cannot limit it to one origin. The vector lib can have different origins. It's free to move about in space. I don't know if that answers your question, Daliso. Then we come to the last special vector, which is the vector unitaire. The vector unitaire, c'est un vecteur de module égal à 1. It's like the smallest, okay, not the smallest is the one that's equal to 0. It's like a vector unitaire. I like to think of them as building blocks. We will see later on. Yeah, you did something similar with Charles yesterday, but we'll see it in more detail, the vector unitaire. But I like to think of them as building blocks. These are the ones that we use now to build on in terms of sizes of the vectors. They guide us the vector unitaire. But for now, what you just need to know is a vector unitaire, like the name or like the name implies, unitaire. It's a unit vector. It's a vector with a size equal to 1. The module is equal to 1. That's that for now. Then we come to the second part, which is repère d'espace. Repère d'espace. Before I get into this, there's what we call repérage in mechanics. Repérage. What does a repérage do?
Excuse me.
Yes, yes.
Starting from the vector libre until the thing we're supposed to start right now. I'm very, very lost. Can you please summarize it once more?
Okay. I'll begin from this last part here, the vector particular, before I come to these three types of vectors. So vector particular, number one, c'est un vecteur nul. Vector nul is a vector with a module equal to 0. It's like its size is equal to 0. That's a vector nul. Then we have a vector constant. It does not change. Nothing about it changes. Its size is fixed. Its direction and its sense, they are all fixed rather. That's a vector constant. Nothing about it changes. It's constant. Next up, c'est le vecteur unitaire. Vecteur unitaire, c'est un vecteur de module égal à 1, ou bien de module égal à l'unité. L'unité is like 1. That's the vector unitaire. So when they say ça, c'est un vecteur unitaire, directly you know that its module is equal to 1. Its size is equal to 1. Then we come to this part. On distingue trois types de vecteurs. So I'll begin with the vector lié, the second one, which is the easiest. Vector lié, it has its origin fixed, its direction and sense fixed, and also its size fixed. So if I have a vector here, this vector AB, vector going from point A to point B, and I'm told that A is the origin of this vector, as we can see, because the flash is pointing towards B. That means it's starting from A. If it's a vector lié, this vector, the origin is always going to be A. It's going to remain at point A, that origin. C et seulement C, c'est un vecteur lié. The direction is going to be in this direction here, from A to B, from A to B. The direction is going to remain like that. The sense, as given by the flash, the arrow, is going to remain pointing towards B, just like that, forever and ever. And its size, if I'm told this size, if I'm told this vector is equal to 10, for example, it's going to stay at 10 forever and ever. It's fixed. That's a vector lié. All four properties of the vectors, the origin, the direction, sense, and the module, they are fixed. They do not change for a vector lié. Then you come to a vector glissant. A vector glissant, it has 3 of its properties fixed with only one thing changing, and that's the origin. That means the direction is going to be from A to B, as we know. The sense is going to be towards B, pointing towards B, as we've seen, and its size is always going to be, for example, 10. If the size of this vector, as I said before, is 10, it's not going to change. What's going to change is the origin. So that means the origin can move from this point A to another point on this support, as I called it before. We call it a support, this line, the line that's carrying the vector, support. This vector is free to slide. That's why we call it vector glissant. It's free to slide on that line. Now, as it slides, then the origin is going to change, because if this vector slides in this direction, obviously the origin is going to move from this point A to another point, maybe somewhere there or another point there. It's free to move about on this support, free to move as long as it's maintaining its direction, its sense, and its module, as long as it's maintaining them fixed. Now, for a vector libre, it's less limited in its movement. Unlike the vector glissant, which is only free to move on this surpôt, only changing the origin, vector libre can move away from this surpôt, can come there, can move to there. It's a free vector. It's free to move around in space. It means the origin can be anywhere. It's an arbitrary origin. Can pick any origin and move the vector there. It's free to move about in space.
Okay, I've understood.
You've understood?
Yes. Thank you.
Also,
Lovely.
try to differentiate for me the difference between the sens and direction.
Okay, that's also a tricky one. I also had trouble differentiating between the direction and the sense. It's a good question. The sens, from the notes we've been given here, from the explanations we've been given here, the sens is indicated by the flash. Okay, so whenever they ask you what's the sens of this vector, it's the flash, what the flash is pointing, or where the flash is pointing. The direction is given by the droite here. So the direction, you can use it, if you want to call it, you can say, maybe this vector, we can call it the vector AB. So we know that the direction of the vector is going from A to B, according to the droite there, the line there. Okay, you can have the sens pointing in the opposite direction, and maybe they've given us a vector, the vector is AB. That means we know the direction is from A to B as indicated by the line, but the sens is what the arrow is pointing at. I don't know if that's clear.
Yeah.
No.
Okay, someone has said no. When we talk about the sens d'un vector, it's given by the arrow, la flèche. So when you want to talk about the sens, just look at where the arrow of that vector is pointing. That gives you the sens of the vector. The direction is given by, the direction is given by the line delta. So in this case, this line delta here that we have, the line delta that we have here is going to give us the direction of this vector. And in this case, it's going from point A to point B. So we can say our direction is AB, from A to B, according to this line here. When you're moving in this line, you are first meeting the point A, then as you continue, you are meeting the point B. So we know the direction is from A to B. Clear?
Oui.
Ok,
Oh,
très bien, c'est compris.
Can you say
Sorry?
that the sense is giving the direction? In other words,
Pas forcément, not necessarily. Sometimes it can give you the direction, and sometimes it can be in opposite directions, so to say. Okay, so we come to the repère d'espace. En mécanique, on a souvent besoin de définir la position ou la vitesse d'un objet. Or, ces grandeurs peuvent avoir des valeurs différentes selon le repère d'espace où elles sont mesurées. Now, what's a repère d'espace? This repère d'espace they are talking about. Un repère d'espace à 3 dimensions, we call it un trièdre, est un système formé par 3 axes non coplanaires. Okay? Coplanaire, it means they are parallel to each other. Liés au un point zéro appelé origine du repère. So we can call all these 3 axes, OX, OY, OZ. They all have the same origin, which is at point 0. We call it OX, OY, and OZ. Le trièdre est dit trirectangle ou Orthonorme. Now this one here, this word here, you have to pay particular attention to it. Autonomy. You see this every time you are doing a question or every time you are learning mechanics. They will tell you soit un repère orthonorme. So you have to understand what they mean by orthonorme. So I wrote something towards the end of the PDF here. So there's three characteristics we have to look at here. Number one, say orthogonal. These words are very important, very, very important. Pay attention to this. Orthogonal. When we say two lines are orthogonal to each other, it means they are perpendicular to each other. They are at 90 degrees. So we have this line here, OI, perpendicular to OJ, according to this angle here, the 90 degrees. That means they are orthogonal. Don't forget that. Orthogonal, it means they are perpendicular to each other. So when we say orthogonal, they are just perpendicular to each other, but the distance from the point or from the origin to E and the distance from O to J, they cannot be the same. What's that's important is they are perpendicular to each other, and that's orthogonal. Next up, we have norme. Norme means their module is equal to 1. So if I say I and J are norme, it means they are vector unitaire. Their module is equal to 1, and they are equal, as it says here, sont égales mais ne sont pas perpendiculaires. So if we just say c'est normé, it means they are of module equal to 1 and they are equal. If they're both of module equal to 1, that means they're equal because they both have a size equal to 1. So orthogonal, they are perpendicular. If they are normé, their size is equal to 1 and they have the same size. So when you say orthonorme, you have mixed orthogonal and normé. You have now orthonorme. That means they are perpendicular to each other and they have a module equal to 1 and their sizes are equal, as you can see from this figure here. So when they say orthonorme, soit IGK in base, orthonorme, it means the base has axes that are perpendicular to each other and they have a module equal to 1. And they have module equal to 1. Is that clear?
Excuse me.
Yes.
I had network problem, so I didn't get what you explained, starting from the repair octagonal until to the last one there.
Okay, I'll say repère orthogonal. Number one thing you have to understand or we have to mention is that a repère has axes. I'm sure in high school you did something like the X or Y plane, not so?
Yes.
Yes, you did the X or Y plane. So you know OX is called an axe and OY was also called an axe. So that whole thing there, we call it a repère. That's what we can call it, a repère d'espace, that OXY. So that means the repère has axes. Now, what we are interested in now is the orientation or the relationship of the axes with each other. So you have maybe OX and OY. So when they tell you un repère orthogonal, orthogonal in French, in English orthogonal, it means they are perpendicular to each other. They are at 90 degrees. They are meeting at 90 degrees with each other. That's orthogonal. So whenever in mechanics you hear someone say un repère orthogonal, it means the axes of that repère are at 90 degrees with each other or to each other. I don't know which proposition is convenient there. They are at 90 degrees with each other. That's orthogonal. Don't forget that, orthogonal. Then when you come to repère normé, it means this one here, the OE is equal to 1. The size, the magnitude, and the OJ, its size is also equal to 1. That's normé. usually use normé when you're talking about une base. We are going to look at the base later on. I'm sure Charles mentioned something similar yesterday, because for a base, it contains the vector unitaire. And we know vector unitaire, the module is equal to 1. So then it's normé. If the module is equal to 1, c'est normé. And if it's normé, it means they are of equal modules, as it says here. Repères normés OI et OG sont égales, mais ne sont pas perpendiculaires. That's normé. They are equal. They both have a module equal to 1, but they are not perpendicular. Orthogonal, they are perpendicular. Then you come to orthonormé. Orthonormé is a mashup of orthogonal and normé. Orthonormé, orthogonal plus normé. That means the properties of orthogonal and normé put together. That means the axes are, number 1, perpendicular to each other. Number 2, they have equal module, and their module is equal to 1.
I have a question.
Okay, Daliso is asking, so seeing, just give me a sec. So seeing these three planes, does it mean we won't expect anything larger than 90 degrees from vectors? Not necessarily, but when you're talking about axes, axes will always be at 90 degrees to each other in the mechanics you'll be doing. But for other angles, they can be greater than 90 degrees because we'll be projecting lines. So you can have a line greater than 90 degrees. But for the axes in a repère, they will always be at 90 degrees to each other. They're always orthogonal. I've never come across a question in Mécanique du point which has got a repère with axes that are not orthogonal. Yes, someone wanted to ask a question. Go ahead.
Exactly. You're talking about the module, which is equivalent to 1. But does the one have a measurement? As in, is it? What exactly are we talking about?
Can you rephrase your question so that I answer it properly?
Like that is the second one, which is the repère nommé. Yeah, those we're talking about them being equal. That's in size, I believe.
Yes, yes.
Yeah, but and that they have to be equal to what is the module, which is it 1?
Yeah, 1.
Yeah, but that one, like, does it have a measurement? Like, what are we comparing it to exactly?
Okay, that's a good question. Now, vectors, here we are looking at vectors in general, but we have specific vectors like velocity is a vector, acceleration is a vector. So when we say unitaire, let's say we are in the case of velocity, it's going to be 1 meter per second. That's the unit, that's 1. When you go into acceleration, it's going to be 1 meter per second squared. When you go into force, the vector force, the unit or the 1 is going to be 1 Newton. Is it clear? Or is that, was that your question?
Yes, it's clear.
Okay, great. Any more questions on autonomy? Silence is taken as a no questions. So that's that about autonomy. I just felt it's important that you guys know what they mean when they say autonomy, because almost all the questions in mechanics, they begin with this. Soit, ça, une base, autonomy. So I just thought it's very important that you guys know what they mean by autonomy, so that you know what properties you are going to use exactly. So it goes on to say, le trièdre est orthonomé direct si les axes OX, OY, OZ sont tels que un tire-bouchon se déplace dans le sens de Z positive. Okay, I'm going to explain this property later on when we start doing the Cartesian planes, the cylindric planes. When we start doing the math, we can skip it for now, okay? The autonomy direct. it's going to be clearer then, because a certain property that's not mentioned here, that's very important on the direct part, because the rest of this part is not so important. I'll explain it later on. C'est bon?
C'est bon.
Oui, c'est bon.
Ok, on avance. La base. Something also important in mechanics, la base. So now we said un repère has axes, as we said. And in mechanics, we'll be dealing with un trièdre. That means a repère with 3 axes, as shown in the figure here. Now they are saying, sur chaque axe OX, OY, OZ, on peut définir un vecteur de module 1 appelé vecteur unitaire. So they're saying soit I, J, K, c'est vecteur, the module of I or E, the module of G or J, the module of K or K is equal to 1. So like I mentioned before, I like to think of these vectors in a base as building blocks, okay? As building blocks, because they are the smallest component, I should say, on a vector that you work with. It's always the unit, the unit. Even when counting, when we're counting, we count in ones, because 1 is the building block of our number system. We say 1 plus 1, that's 2, plus 1, that's 3, plus 1, that's 4, plus 1, that's 5. So in that case, 1 is like building block there. It's the same things for same thing for these. These are the vectors that are found in a base. When you're moving along the x-axis, you'll be moving in terms of I. So when we move 1 step, we move 1i. When we move another step, we'll move 2i. When we move another step, we'll move 3i, ainsi de suite. When you come to the y-axis, we'll be moving in terms of j's. When we move one step, we move 1j. Second step, 2j. Third step, 3j. It's like we're building in terms of j's. Just like when you're building a house, you use blocks, not so. You put one block, you're up by that size. You move another block, or you put another block, you're up by that height. You put another block, you're up by that height. That means those blocks are using there, the building blocks, so to say. It's the same thing for the bus. The bus is like the building block for your movements along these axes. And they are always equal to 1. In a bus, the module is equal to 1 for that vector there. So as you can see, he has indicated the module of I is equal to the module of J is equal to the module of K is equal to 1, because they are the building block, they are unitaires, they are equal to 1. L'ensemble de ces 3 vecteurs I, J, K est appelé base du repère R. So that's that about the base. So from now on, we'll be working with these bases, so to say, the base, we'll be working with them. Whatsoever vector we are going to represent, we are going to represent it in terms of these bases that we've looked at. So now we're saying représentation d'un vecteur. Soit un vecteur V égale à OM, what you are doing yesterday in electromagnetism, the OM being equal to XE plus YG plus ZK. I don't know if you guys know how to interpret this, but what they are telling you when they give you a vector like this one, XE plus YG plus ZK, is like they're saying, we shall begin with the x-axis number 1. Move x's or x steps on the x-axis. So you move 1, 2, 3, x on the x-axis. Then they tell you plus YG. So now they're telling you, now move y steps on the y-axis. So we'll move parallel to the y-axis. We'll be going in this direction until we move y. So maybe y, we're meeting it there. And then they tell us now, finally, you are moving z steps parallel to the z-axis because of the car. So now we'll move up parallel to the z-axis, and maybe we'll have our OM somewhere there. So if you have an example, say you are moving 3i plus 4j plus 5k, you will begin. The I is somewhere here, so you will move 3 i's here. 1i, 2i, 3i. Then you will move 4j, so you will move parallel to the y-axis. 1j, 2j, 3j, 4j. You'll meet it somewhere there. Then you'll move 5k's parallel to the z-axis. So you'll be going up this time around now. You'll move 5k's. So you'll say 1k, 2k, 3k, until you reach 5k. And maybe you have your point OM there. It's like they're just telling you move one step forward, move one step to the left, and then move one step up, or move one step forward, move one step to the right, then move one step down. That's how you interpret this representation of the vector. Kindly repeat that part. The representation or the bars.
The representation, okay, how you are moving, yeah, how you are moving the vectors.
Okay, so there's two questions here. How and asking letters represent quantity of movement, the x, y, and the z. So how we're moving? We have our vector here. Our vector, we've been told the vector is OM equal to XE plus YG plus ZK. So what they're telling us here is move X steps on the X-axis, because the vector unit there for the X-axis is the I, as you can see from the figure here. So when they tell you XE, they're telling you move X steps on the X-axis. So you move X steps on the X-axis, then plus YJ. Now they're telling us move Y steps on the Y-axis or parallel to the Y-axis. So we'll move Y steps, Y-axis will be going parallel to the Y-axis here like that. Then finally, they tell us to say move Z steps to the parallel to the Z axis because of the K. The K is the vector unitaire for the Z axis. So now we'll be moving Z steps parallel to the Z axis. So we'll move Z steps going up like that. I put some questions down here. Vectors, instead of using things like X, E, maybe those things are confusing you guys. You can, we can use this example here. Can use this example here, saying soit un vecteur U equal to 5i plus 2j plus 3k. So when you have such a vector, now they're telling you to say, plot this vector on a Cartesian plane. On the plane, you first move 5 steps on the x-axis, then you move 2 steps on the y-axis, then you plot those two, and then you move 3 steps on the x-axis, which is also not the x-axis, but the z-axis, which is actually going up because it's a vertical axis. So you move 3 steps going up. I really wish I could draw for you guys to show you, but we are limited. So I'll encourage you guys to be imaginative, more or less. Yes, Lawrence, like 3J, 5I, exactly that. Someone asked the question, it was Cherumlenga, if I remember. Is it clear?
Yes, it's clear. Thank you.
Okay. Someone has raised their hand. I wonder who. Says Chico Pao. Is your hand still up? Or it's clear? Yes, so that's the representation of the vectors and what they represent. Okay, that's that. It's like you're saying 5x, 3y, and 6z. So you plot them first on the horizontal plane, the xy plane, and then you plot it against the z-axis and you get your point OM using this representation, xe, yg plus zk. Now, we come to the module. The module, this is a formula for finding the module. Yeah, so when you're given
a question,
you have a question? Yeah.
How are you to know direction to move? For example, you have to go vertical or horizontal.
Whether to go vertical or horizontal, you'll be guided by the bases here. So when they tell you to say E, XE, it's along the x-axis, according to this diagram. E is almost always representing the x-axis, always. So when they tell you XE, you are moving in the direction of the x-axis. When they tell you YG, the G is used to represent the y-axis. you'll be going in the direction of the y-axis. Then when they tell you z car, you'll be going in the direction of the z-axis. Now you'll be going up the vertical plane. The z plane is the one that's vertical. Is that clear?
Yeah.
Okay.
No.
How is that for stating that all the bases EG and K are equal to 1 applied? How is it applied? Okay. So the rule that they are, is it the norme you're talking about? The one that's asked the question in the chat. Is it the rule for the norme?
No, just there on the what? On the basis. It's that you said that the modulus of
Yeah,
all the three bases, they are equal to 1.
it's equal to 1. Yeah, they're telling us
Yeah.
that they're the vector unitaire. So for why they are equal to 1 is because they are building blocks, you see. They are just guiding us. They are just guiding us in terms of direction, which direction to go. So if you give them a value of 2, they will be doubling the size of the vector when they are multiplied, like when you say xe, and the module of e is equal to 2. When you multiply x by 2, it's going to give you 4. So you'll be changing the size. So we're using 1 so that we do not modify the size of the vector, okay? So that when you multiply by 1, the size of the vector is not modified, it's not changed, it's not tampered with in any way. The e is just going to maintain its property of guiding us in terms of the direction to follow as we study the movement. That's why we are using 1. You get it?
Yeah, somehow, but yeah, I'm not.
You are not satisfied with the answer?
Yeah.
Okay, let me try to respond to that again. Lawrence is asking, do they ask weighty questions in Mécanique du point, or we just focus on the calculations? Well, you have maybe an exercise with 5 to 10 questions. Maybe just one of them is going to require you to explain something. Let's ask you, why is this like this? But mostly it's calculations.
All right, thank you.
Depends on your professor, though. I am at the FST. They don't really ask us a lot of explanations in mechanics, but I don't know how it is at the ENSA. Perhaps the professor wants to see if the student understood the concepts he was giving them. So it's best to just understand everything.
All right.
Okay, good. Are the letters EGK constant, or other letters may be used? Other letters may be used. They may be used, but just for uniformity, most professors and most books use EGK. But it's possible to use other letters. But for uniformity, we just use those letters EG and K. Then back to David's question, how we apply the property modulus of all the base vectors equal to 1. So these base vectors, when we use them in this case here in the representation xe, yg plus zk, they are showing us the orientation or the direction in which the vector has to go that number of steps. So let's say I have 5e. Okay, I've been told the vector moved 5 steps times e. They are telling me that the vector moved 5 steps on the x-axis. So I know that the vector moved 5 steps in the direction of the x. This e is not going to change anything in this case because 5 times 1 is going to be 5. Now imagine, to understand some of these things, you try to pose the opposite. If they tell you the vector unitaire is equal to 1, and you're asking yourself, but why is it equal to 1? To answer that question, try asking yourself, what if it was equal to any other answer but 1? Let's say if it was equal to 2, or maybe it was equal to 0.5. And then they have given me this representation, 5e, and it's equal to 0.5. When you multiply 5 times that 0.5, it's going to give you 2.5. It's going to change the number of steps you're supposed to take when you're moving there. Or when you're building, since I said the vector in it there are building blocks, so instead of building in ones now, you'll be building in 0.5s, which is also another complicated system of counting. Imagine you'll be counting 0.5, 1, 1.5, 2, 2.5, 3, 3.5. So just counting in the conventional sense, the 1, 2, 3, 4. You now go into the complicated counting system of 0.5s because your building block is going to be at 0.5. So they are equal to 1 because they are our building blocks, and it's going to be easy to take note of the movements of our vector, the amount of steps exactly it takes, because we are counting in ones. So when you say it's moved 5e steps, so it's like 1, 2, 3, 4, 5, because the e is equal to, the module of the e is equal to 1. So you're counting in ones. 1, 2, 3, 4, 5, and you're taking note of the movement, sorry, of that vector so easily. Using any other module for the base apart from 1 is going to complicate your work because you will no longer be counting in ones. David, I don't know if that's clear.
Yeah, it's clear.
Yeah, sure?
Yeah.
No.
Okay, lovely. Someone said no. Was that a no I heard?
No. Répétez s'il vous plaît.
Okay, the part I'm from explaining, or what should I repeat exactly, sir?
That's you are from explaining.
Okay, so David asked the question, said, but what's the application or the significance of the modulus of the base vectors e.g. and k being equal to 1? So I was telling him that, as I mentioned earlier, try to look at these base vectors as building blocks, okay? Things you use to count exactly the movement or the amount of steps that vector takes. And then I said, you're asking yourself, but why does it have to be equal to 1? So I said, for you to understand that, try asking yourself the opposite and see if there's a fault somewhere there. So I said, let's try to pose that the modulus of these vectors is equal to 2, for example. So when you come here, this I is equal to 2. And they've told us that the vector OM has moved, for example, 5I, okay? So instead of counting in ones like we'd normally do, we'll be counting in twos this time because the vector I is equal to 2. So you'll be counting 2, 4, 6, 8, 10, yeah, up to 10, meaning you've made 5I. That's a bit more complicated than counting in ones if the I is equal to 1, where you just say 1, 2, 3, 4, 5. So the work is going to be more cumbersome. It's better we are just counting from 1 and then we are just adding ones, 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 like in the normal conventional sense of counting. That's the significance of these base vectors being equal to 1, because they are what's helping us take note of the movements. They are what we are using to count the steps or the movement of something. As I said, these vectors, as we are studying them now, they are general. But if we go more specifically, we can get quantities like velocity, okay? We start getting velocity. Maybe you have velocity equal to 5 meters per second squared. And the modulus of these base vectors is equal to 2. So for you to do 5 meters per second squared, instead of just counting 5 steps, you'll be counting 10 steps this time because your base vectors, your building blocks are equal to 2 instead of 1. So we keep it at 1 so that we are not changing the magnitudes of anything. And even as we are keeping track of the movements, we are counting them in ones. It's easier that way to count, to take note of the movement in ones. C'est clair? Ou bien non?
Merci, c'est clair.
Ah, je vous en prie. Is the final vector direction supposed to be joined with the other vectors, or we have to leave it hanging on the X or X or Y or Z? MacBook, I don't understand your question exactly. Can you try to explain it more so that I answer properly? Tambafia is saying repeat, please. You are also asking why the base vectors have to be equal to 1. Tambafia, that's your question too.
Sorry, I didn't understand what you were explaining, your previous explanation. I didn't get it.
Okay, my previous explanation, why the base vectors have to be equal to 1. Okay, let me just put it bluntly. On grow, we can just say it's because they are the building blocks. It's what you're using to count. When you count 1, 2, 3, 4, 5. So even as you are counting on these axes, the X and the Y axis, you will be counting still 1, 2, 3, 4, 5, 6, and so on. That's why we keep the base vectors at size equal to 1, so that we can count in ones. Simply put. Is it clear?
Yes, it is.
Okay, lovely. MacBook asked a question. MacBook, your question was not clear, but as we are waiting for you, make the question clear. We can look at the module. So we are still with this same vector here, the vector V. And one thing, never forget arrows when you're dealing with a vector. These arrows on top of the letters. When you say V is a vector, even if your answer is correct, if you leave out this arrow, your answer is going to be wrong because it's no longer a vector. Even if it's just on this I, you have to indicate the arrow. À chaque fois, toujours, c'est obligatoire. If you leave out the arrow, you lose marks. So take care. Never leave out the arrows when you're denoting vectors. Very, very important. So we have this vector here, V equal to xe plus yg plus zk. When they ask you to calculate the module or the size of this vector, you use this formula here. You just get the coefficient of the I, you square it, plus the coefficient of the j, you square it, plus the coefficient of the z, you square it, and the answer, you square root it. Then you have the module. Ça, c'est facile. C'est une formule à retenir. The formula you just have to know by heart. Just keep it in your mind and in your heart that the module, you calculate it like this. Then sometimes the module can be denoted by one line like this, one line on the left, one line on the right. Sometimes you use two lines on the left, two lines on the right. C'est la même chose. It's the same thing, don't be confused. It's just a notation that's different here. Then we come to produit scalaire. Example, please. Okay. Example is for the module Noto, iPhone.
Oui.
Okay. So I'll come to this vector here. I tell you to say, calculate the module of U. You've seen U the way I've written it up.
Yes.
Yeah, U is equal to 5i plus 2j plus 3k. So if I ask you to calculate the module of this, what you're going to do is, it's going to be the module of U is equal to, you write one big square root, and then inside the square root, you write 5 squared plus 2 squared plus 3 squared and work it out. Now tell me the final answer you get. You have a calculator with you?
The what?
A calculator.
Yeah, I do have a calculator. What did you say?
The module is going to be equal to 5 squared plus 2 squared.
A minute, 5 squared. Five squared
plus 2 squared plus 3 squared.
38.
38. Then you square, it's the square root of 38.
Which is 6.1644.
And that's your module. Tout simplement. You just get the coefficients, you square them, add them, and the square root of the sum. Then that's your module.
Okay, so when they are moving, maybe on the X plane.
Uh-huh.
Are they moving as coordinates or it's just one number?
They will move as coordinates because if it moves, its coordinates are going to change.
But how come we just used 5 instead of a full coordinate?
How come we just used 5?
Yeah.
What's the full coordinate supposed to be?
I don't know, like 5,2, something like that.
Yeah, those are the coordinates. The coordinates in this case, it's 5, 2, 3. Those are the full coordinates of the 3-dimensional vector we're dealing with here.
Oh,
Yeah,
okay,
so
I
we've used all 3.
understand.
Yeah, you get now?
Yes.
Okay, lovely. Everyone else, c'est clair?
Oui.
Oui. Okay. I'm here if you have any questions. I don't want anyone to remain behind, so if you have any question, feel free to ask. That's why I'm here. It's for you guys.
Please get back to that example. I'm sorry, I lost connection. So just found the example has been done and we are moving it.
Okay. So you know the formula for calculating the modular? You've seen it?
Yes, I've seen it.
This one, the square root of x squared plus y squared plus z squared.
Plus.
Yeah. So when you come to the question here, we have our vector u is equal to 5i plus 2j plus 3k. Yeah?
Yes.
And I say find the magnitude or the module of u. So from the formula, we have the module of u is equal to the square root of x squared plus y squared plus z squared. So what you're going to do here is you're going to get your x coordinate. Your x coordinate is going to be the coordinate following the I base vector, not so. So it's 5. So it's a 5 squared plus what follows is y squared. That's your y coordinate. Your y coordinate is the coefficient following the j. Okay, so it's going to be 2. So it's 5 squared plus 2 squared plus z squared. The z there is following the k. So we get 3 squared. So we have 5 squared plus 2 squared plus 3 squared. When you add those squares, you will get 38. Then you square root the entire answer according to the formula. It's going to give you 6 point something, and that's going to be your module. So you just get the coefficients, all 3 coefficients, you square them, you add them, and find their square root. Stuff.
All right, thank you.
Awesome stuff. Then there's something I'm going to explain to you guys here. I want you to pay attention because I'm going to ask you a question and I'm going to expect an answer from you guys. I want you to reason. I don't want you guys to just follow me. So I'm going to ask you something. It's trigonometric. Yeah, just some mathematics you have to apply. So pay particular attention as I explain this part. So we've reached the produit scalaire. Le produit scalaire des deux vecteurs u et v est le scalaire u. So when you see two vectors, you have the vector u and the vector v, and you have a dot in between them. They're asking you to calculate the produit scalaire. Okay, we call it scalar product, produit scalaire. So when you see this u, a dot, and v, you know they're asking you for a produit scalaire. How you read this is u scalaire v. So this dot, you're going to read it as scalaire. U scalaire v, U scalaire v. And the formula is given by this. U scalaire v is equal to, this is something you should know by heart. Understand it first and then keep it in your mind. Very important formula. U scalaire v égale module de U fois le module de v. Now, I know it's written equal to here. It's not supposed to be equal to. I tried to cancel it out. It's not supposed to be equal to. It's supposed to be multiplication. Fois again, cosinus or the cos of the angle between the two vectors. You have these vectors here, U and V, according to the figure. The angle between them is this one, the alpha. So the produit scalaire of these two vectors is going to be U, le module de U, fois le module de V, fois cosinus alpha. Cosinus of the angle between them, alpha. And you have it. There you have it. That's your formula. So when you have two vectors represented like that, and you tell you to calculate the produit scalaire, you get the module of one vector multiplied by the module of the other vector, then multiply that product by the cosinus of the angle between them. It's clear, the formula.
Oh, it's clear.
Yeah, we call it expression analytic, this formula here. Then we come to this next line here. This is a particular case. So you have a vector E with the coordinates x1, y1, z1, and then you have a vector V with the coordinate x2, y2, z2. So the product scalaire of these, if you're just going to get the formula, the answer is going to be, you are going to multiply the x coordinates, you multiply x1 times x2, plus the y coordinates, you multiply y1 by y2, and then you get the z coordinates, you multiply z1 by z. I know it's written z3 here, it's supposed to be z2, and that's your answer when you add them, when you have coordinates like these ones here. So, like in the question we had at the end here, the example we are using, if I've got two vectors like these ones here, U and V, and they say calculate product scalaire, what you're going to do is you get the coefficient for the I, the x coordinate, you multiply it with the x coordinate in V, it's going to be 5 times 1, plus the y coordinate in U, multiplied with the y coordinate in V, it's going to be 2 multiplied by -4, it's going to give you -8. So you have 5 minus 8, which is -3. Then finally, you add it with the product of the z coordinate. So you say 3 multiplied by 1, it's going to be 3. And then 3 minus 3, it's going to give you 0. So the product scalaire is 0 in this case. How convenient. Then, now, some of you are wondering, but why is the expression like this? Why is the formula like this? I'm sure you are wondering, or is it just me that's wondering? Why are we just multiplying the x coordinates plus the y coordinates plus the z coordinates? The answer is simple. It's actually, what you're normally supposed to do is you're supposed to multiply all the coordinates together. So you'll be multiplying x1 times x2 plus x1 times y2 plus x1 times z2. The way you expand polynomials, when you're expanding polynomials, maybe you've been given x plus y, just give me a sec, x plus y multiplied by y plus z, and I tell you to expand that. You're supposed to multiply all the terms together. Come in. Yeah, sorry for that. Someone came knocking. You are going to multiply all the terms together and get your final answer. In this case, we'll be multiplying all the terms using the product scalaire together. See what our answer is going to be. So when you begin here, you have x scalaire like x1 scalaire x2, x1 scalaire x2. So we'll come to our formula, the formula that we had here, this one. So we have x1 scalaire x2. So we'll write module the x, module the x1, module the x2 fois cosinus of the angle between x1 and x2. Now, what's the angle between x1 and x2? Both of them are found on the x-axis. So the angle between them, this is where now you have to apply your trigonometry here. This is where you apply it now. x1 and x2 are both found on the x-axis. That means the angle between them is either 180 degrees if they are in opposite direction, or 0 degrees if they are in the same direction. Here, there's no difference in them for us to have an angle. So what we'll be having here is cosinus of 0, for example. Cosinus of 0 is, what's the cosinus of 0?
1.
1.
Yes, the cosinus of 0 is 1. So meaning x1 scalar x2 going to be module of x1, which is as x1 multiplied by x2 multiplied by 1. So you have x1 and x2, just like that, x1 times x2. Is the first part clear?
Yeah.
Okay, then now you multiply, we'll now calculate x1 scalar y2, because we have to multiply all the terms by each other, like in the normal multiplication you do. So you now have x1 scalar y2. So you come here, you say x1 scalar y2. It's going to be equal to the module of x1 multiplied by the module of y2 times the angle between x1 and y2. So x1 is found on the x-axis and y2 is found on the y-axis. Now, one thing we know about this hot pair is what? It is autonomy. And if it's autonomy, we know that it's orthogonal. And if it's orthogonal, we know that all the axes are at 90 degrees to each other. That means the angle between x1 and y2 is equal to 90 degrees, not so?
Yes.
Yeah, the angle between x1 and x2 is 90 degrees. So here we'll be having cosinus of 90 degrees. What's the cos of 90 from trigonometry?
0.
Cos of 90 is 0. That means the product scalar of x1 and y2 is going to give you what? 0.
0.
Not so, exactly. It's going to be the same for x1 times z2 because they are also perpendicular to each other. Then y1 and x2, same thing. y1 and z2, same thing. They're all perpendicular to each other. So they'll be giving us 0, 0, 0s. So all we are going to be left with is the terms that are multiplying each other and are on the same axis because the angle between them is 180 degrees. So we just have x1, x2. When you multiply y scalar, y1 scalar, y2, we'll have y times y1 times y2, sorry. Same thing for z. The rest will cancel, the rest will nullify themselves. Their product scalars are going to be equal to 0 because cosinus of the angles between them is equal to 0. Oh, Lawrence is saying that's deep. I'm glad you guys are following. So that's why the expression when you have two vectors like that remains this one. And this is the one we'll be working with mostly. It's going to be this one. So when I give you two vectors, sorry, not angles, like in the x-axis here, I have u and I have v, and I tell you calculate the product scalar of u and v. You just multiply same term, coefficients 5 and I, 2 and -4, 3 and 1, and then add them, and that's going to be your product scalar because the rest is going to simplify according to trigonometry. This is why I emphasized at the beginning that if you've not done any trigonometry, you should do it because you have things like this that you only prove using trigonometry, that you only understand using trigonometry. Is everyone on the same page as I am so far?
Yes.
Yes.
Okay, lovely. So we come to the properties of product scalar. These ones you just have to know them. Number one is that the product scalar is commutative. You guys know what this means, commutative. A plus B is equal to B plus A times B is equal to B times A. Product scalar is the same thing also. U scalar V equal V scalar U. Even if you swap them, the answer remains the same. Then they're saying le produit scalaire est distributive par rapport à l'addition. That means if you have U scalaire entre parentheses, V plus W is going to be equal to, if you expand these and add them, the answer is going to be the same. That's what they mean by distributive par rapport à l'addition. Because the how do you say it in English? Distributivity comes in two types, distributivity par rapport à l'addition et par rapport à la multiplication. If you remember the properties you are doing in secondary school about commutativity, being distributive and also being associative. So distributive par rapport à l'addition it is, but par rapport à la multiplication it's not distributive. If you have U scalaire V scalaire W, it's not the same as U scalaire V scalaire W. If you change the orientation of the brackets, the answer changes with it if you're dealing with multiplication. But if you have addition in the parentheses, even if you expand it, the answer is going to stay the same. Then I would like one of you who's following well to try and explain to me, or to try and explain to us why the next property is so. It's trigonometry, especially for you guys that did trigonometry in high school who know trigonometry well. They are saying the product scalar of U and V is positive or is greater than 0 if alpha, the angle between them, is between 3 pi over 2 and pi over 2. Can someone try to tell me why this is so? Why the product scalar is going to be positive if the angle is between 270 and 90 degrees? That means goes round from 270 all the way to 90 degrees. That part between 90 and 270 is excluded. Just the part outside 270 or after 270 and before 90. If the angle belongs to that, the product scalar is going to be positive. Why is that so?
Because cos theta is positive in the fourth quadrant.
Yes, in the fourth quadrant. And in what other quadrant?
The first quadrant.
The first quadrant, exactly. Because the first quadrant is before 90 degrees and the fourth quadrant is after 270. So cos alpha is going to be positive in those two intervals. That's why the product scalar is positive there. That's brilliant. Who's that responded?
Tambachi.
Okay, that was well done. That means the next one is also going to be clear. Between 90 and 270, the product scalar is going to be negative because cosinus of alpha is negative in that interval. Clear?
Yes.
And then I also need you guys to explain this one for me also. That's from trigonometry. That's from your understanding of trigonometry. U scalar U equal the module of U squared from this formula here, from the formula here that I told you guys you should know. If you have U scalar U, it's going to be equal to the module of U squared. Why is that so?
I think it's because the cos of 0 is 1, because if you're given two same vectors, there's no difference between the angles.
Parfait, ça c'est parfait, exactly. The angle between U and U is 0 degrees. So you have cos of 0, which is 1. So this cosinus part cancels out. So you just have U modulo of U, scalar modulo of U, which is not scalar, multiplied. Here they use both scalar and multiplication, they use dots, so don't get confused. So you have U times U, which is U squared. And that's why U scalar U equal module de U. And the last one again, someone to help me explain it. Si U et V sont perpendiculaires, U scalaire V égale à 0. Let's go. Why is the product scalar going to be equal to 0 if they are perpendicular? If the two vectors we're dealing with are perpendicular?
Cos 90 is 0.
Exactly, cos 90 is equal to 0. The angle between them is 0, so you have modulo of U multiplied by the modulo of V multiplied by cosinus of 90, which is 0. So the entire expression is going to nullify, and we are going to have 0 as a product scalar. So that's that about the product scalar. Then we also have these ones here. Dans une base, if you have une base EJK, one thing we know about the base is that these vectors are equal to what? They're equal to 1, not so. They're module. is equal to 1. So now, if you have E scalaire E, J scalaire J, K scalaire K, they are going to be equal to 1 because you have module of E multiplied by the module of E multiplied by cosinus of the angle between them. The angle between them is 0. The module of E is going to be equal to 1. The module of E again is going to be equal to 1. We know this because they are in bars. Multiplied by cosinus of the angle between them, which is 0, we'll have 1 times 1 times 1, which is equal to 1. Same thing for G. G scalaire G, you have module de G fois module de G fois cosinus of the angle between them, which is 0. So you have 1 times 1 times 1 times 1, which is going to give us 0. Then you come to these ones, E fois G. We already looked at these. They are orthogonal. That means they are 90 degrees from each other. So the cosinus of the angle between them is going to be equal to cos 90, which is going to be equal to 0. So the product scalaire of E fois G and G fois K and E fois K is going to be equal to 0. That's from trigonometry. Kindly repeat the properties. Okay, properties of the product scalaire. Property number 1 is that product scalaire is commutative. If you want to practice some mechanics so far that we've done, maybe tonight you want to practice, try proving these properties. So we show you the product scalaire is commutative. Try formulating two vectors. You get maybe E, you give it any value. You get V, you give it any value. And then find the product scalaire of the two of them. Maybe this time you do E scalaire V, you calculate the product scalaire, you get your answer. And then you get V scalaire E this time around. Start with V and then E. Then get your answer. Then see if the answers are the same. And you know, okay, for sure, it's commutative. If the answers are wrong, then you know that, okay, I've made a mistake in my calculation somewhere. Let me retry and do the product scalaire so that I get a hang of it. So number 1, it is that it's commutative. That means E scalaire V is equal to V scalaire E. If you swap them, the answer remains the same, the order of the operation. Number 2, it is that the product scalaire est distributive par rapport à l'addition. Normally, when you have when you say something is distributive, you have like E times something in the brackets. So if you work out this, if you begin by adding the two vectors, By the way, when you're adding two vectors, you just add like terms. You can't add 5E plus 2G. They are not like terms. So you can only add 5I plus something I, something G plus something G. The way you used to do it in mathematics, order like terms, then you add them. It's the same thing for vectors also. You only add like terms, those with the same variable. You can't add 6x plus 5y. They have different variables, but you can add 6x plus 3x. There you get your answer. So you try adding the two of them first. Then when you add them, you get your final vector. Then you calculate the product scalaire of U and that final vector. It's going to be equal to, if you had calculated U scalaire V, first of all, then you calculate U scalaire W, secondly, you expand it in other words, and then you add your two answers. The answers are going to be the same because it's distributive. This is a property for distributivité par rapport à l'addition. It's like this. It's an algebraic property. You do this in algebra also. Then the produit scalaire n'est pas associatif. Ce n'est pas associatif. Do you guys remember the associativity from secondary school? It means if you have an expression like this, you have you have an operation, between brackets, and you're doing something to it outside. If you move the brackets to something else in that same operation, the answer is supposed to be the same if it's associative. If, let's say, you have between parentheses, you have 2 plus 4, and then outside the parentheses, you have plus 6. You add 2 plus 4, first of all. It's going to give you 6, because you begin with what's in the brackets from BODMAS, and then when you get 6, you add it to the 6 outside the brackets, you get 12. Or if you want, you can move the parentheses. In the first question, or in the first equation, we had 2 plus 4 between parentheses. This time I can leave the 2 outside the parentheses, and then I'll have the 4 and the 6 between the parentheses. So this time I'll begin with 4 plus 6, give me 10, plus the 2 outside, it'll give me 12. So there you know that addition is associative. That's what the associativity means. When you move the parentheses, the answer remains the same. And for the product scalar, it's different. If you begin with U scalar V, then you do the scalar of the answer by W. It's going to be different from when you begin with V scalar W, and then you do the scalar of U outside. It's not associative. That's what associativity is. I hope that's clear. And then they are telling us here in the next property, this is now trigonometry, an application of trigonometry. They are saying U scalar V is greater than 0. It's positive if alpha, the angle between them, is between 3 pi over 2, which is 270 in degrees, and pi over 2, which is 90 degrees in, which is 90 degrees. What they're trying to tell us here is that if the angle between them is found in the first and the last quadrant, as our comrade told us, it's going to be positive, because we know this, that if angle is found in the first and the last quadrant, the first quadrant goes from 0 to 90 degrees. The last quadrant goes from 270 degrees to 360 degrees. Their cosinus is positive. So if the angle is found in those quadrants, it's going to be positive. So our product scalar is going to be positive. On the other hand, if the angle is found between the second and the third quadrant, between 90 and 270, cosinus there is negative. That means the product scalar is going to be negative, because the cosinus of the angle we'll be getting is going to be negative. That's that about is the quadrant. We come to the second last property. Second last property, they're saying U scalar U égale module de U carré. Why? Because the angle between U and U is equal to 0. It's the same vector. The angle between it is 0. So cosinus of 0 is 180 degrees. Sorry, not 180 degrees. It's equal to 1. I'm sorry, I've spoken so much. I'm trying to get that. Cosinus of 0 degrees is 1. So it's like you'll be having module of U multiplied by the module of U multiplied by 1. So we'll just remain with module of U times module of U, which is equal to module of U au carré. That's what the squared means. Then lastly, we are saying if U et V sont perpendiculaires, the angle between them is 90 degrees. Their product scalar is equal to 0. Why? Because cosinus of 90 degrees, from the expression analytic here, cosinus of 90 degrees is 0. So you have U times V times 0, which is just going to give you a 0. That's why the product scalar of two angles, of two vectors that are at 90 degrees to each other, or that are perpendicular to each other, is equal to 0. And always remember this, property, because you will be calculating the product scalar when we start doing cinematic and dynamic. When we get into the real stuff now, you'll be doing product scalar. So you have to watch out for these zeros, these expressions that give you 0. You have to watch out for them because they simplify your work. Imagine you're trying to calculate something, you spend like 15 minutes trying to calculate it, then you find the answer is 0, when you could have just known from the property that, okay, this is going to give me 0. And you spare yourself that 15 minutes, you work on something else, and you get more marks in the exam. So watch out for these things that give you zeros because they simplify your work. Is it clear, properties?
Oui, c'est clear.
Okay, it's clear. Lovely, lovely. You guys have even gotten this part on the base vectors, why E scalar E is equal to 1 and why E scalar J, G scalar K, E scalar K is equal to 0. You've understood why this is so. No. Okay. Why this is so? Again, it goes back to the expression, this expression here that we have here. So let's say I've got E scalar E. So E scalar E is going to be equal to module of E times module of E times cosinus of angle between E and E, which is equal to 0. So it's cosinus of 0, which is 1. But base vectors, when we're doing base vectors, we said the module of E is equal to what? The answer, see if you guys have been following, module of E is equal to going once, twice, no one?
1.
Yes, module of E is equal to 1. So it's like you have 1 multiplied by 1 multiplied by 1. So the answer is just going to be equal to 1. That's why E scalar E is equal to 1. The same thing for G. It's going to be module of G fois la module de G fois cosinus of the angle between the two G's, which is 0. So it's going to be 1 times 1 times 1, which is equal to 1. La même pour K. That's why E scalar E is equal to G scalar G is equal to K scalar K. It's equal to 1 for the base vectors. When you come to E scalar G or G scalar K or E scalar K, these base vectors, they are orthogonal. This set here, it's orthogonal. They are at 90 degrees from each other or to each other or with each other. I don't know which one exactly. Yeah, but they are all perpendicular. The angle between them is 90 degrees. So you'll be having cos 90, cos 90, cos 90, cos 90, cos 90, and we know cos 90 is equal to 0. That's why E scalar G is 0, G scalar K is 0, and E scalar K is equal to 0. C'est ça. Is it clear?
C'est clear.
Lovely. I've already explained this expression here. So we can go to the application. That's the last part we'll do. Then tomorrow we'll continue with, since it's almost time, tomorrow we'll continue with the product vectorial. We'll end here on the application. So they are saying if you have two vectors, like the vectors we've been dealing with so far, okay, you have E, you have two vectors, you have one vector E, it's oriented this way, and you also have this vector down here, E, oriented this way. It's going like this vector E. Now, when they ask you to calculate E scalar E, or the product vectorial of two vectors, what exactly are you calculating? I'm sure some of you must have been wondering, but what's this we're calculating? So now this is the graphic representation of the product scalar. So when you have two vectors U like that, and you have a vector E, and they tell you to calculate product scalar, product vectorial of U and E, you have to project a line starting from U, the extremity of U here, at the flesh, at the arrow, the head of U. You project a line towards the other vector in the expression, which is E. It's supposed to be at 90 degrees. The line you're projecting is supposed to be at 90 degrees to this other vector here. So if we have E scalar E, we will start from U. We are going to project a line from U down to E here at 90 degrees. So when we project that line, the product scalar is going to be this line here on E, starting from the origin down to that line we have projected, this distance here. That's what the product scalar represents. It's very useful. We'll see when we do the product mixed. Yeah, when we do the product mixed, you'll see where this comes in handy. It's very useful. But the product scalar simply is just the distance from the origin to the projection on this vector E from U. So they're saying la projection d'un vecteur U quelconque sur un axe orienté delta de vecteur unitaire I est donné par cette projection de U dans la ligne delta ou bien dans le droit delta égale à U scalar E. So you project a line from the extremity of U down at 90 degrees. That's what's important. So the projection is supposed to be at 90 degrees to the other vector here, E, and starting from the origin down to that line that you projected, this distance here, that's what U scalar E represents. So from here we can see the angle between E and alpha, E and E is equal to alpha. We can say it's equal to alpha. So we have cosinus of alpha being equal to, when you change the subject to the formula, when you get this part here of the formula, you have U scalar E equal to modulo of U times the modulo of E times cosinus alpha. So we just make cosinus alpha subject of the formula by dividing this part here, the U for the E over the U scalar E. You get that. Or, on sait que le module de I égale à 1. So this is just equal to 1. So we'll just be left with modulo of E down here. So you have cosinus alpha being equal to this in this special case here. Finally, le cosinus de l'angle que font entre deux vecteurs U et V, when they ask you to calculate the cosinus of the angle between two vectors, so sometimes you might need the angle between the two vectors to continue calculations. You simply just change the subject of the formula from this expression that we have here that we know and love. So we'll just say cosinus of alpha is going to be equal to U scalar V divisé par module de U fois le module de V. Then if you write it explicitly, we know that U scalar V is equal to this. We already proved this. And then we know the module of U is equal to this. It's just the coefficients of U, x1 au carré plus x2 au carré plus x3 au carré. And then V, the same thing, la même chose. It's going to be y1 au carré plus y2 au carré plus y3 au carré. These things we already know them, the module and the formula for the produit scalaire. So the word base is 90 degrees. No, 90 degrees is perpendicular or orthogonal. You can have a base that's not, to specify that the base is orthogonal. That's when you say, or that's when you suppose that the axes in the base are at 90 degrees to each other. If they tell you that it's orthogonal, mostly they'll tell you it's orthonorme. But we know that in orthonorme, there's orthogonal and there's norme. So if they've told you that the base is orthonorme, you know that they are at 90 degrees to each other. It's not always that they are like that. They have to specify that it's orthogonal. But what I said is, in every case I've made in Mécanique at this point, I've done 2 modules of Mécanique in them, Mécanique du point, Mécanique des solides, all the bases I've worked with in all the TDs, in all the past exams, and in the exams I've had myself. The bases were orthonorme always, so we just take them as 90 degrees. We are no longer dealing with Z. We are dealing with Z. I don't understand the last part here. No longer dealing with Z, but we are still dealing with it. We're still dealing with three-dimensional vector.
As in during the projection, the letter Z is not there.
Oh. No, it's only because this diagram they've drawn here, it's looking like it's 2-dimensional. It's looking like it's just X and Y, but normally it's 3 dimensions. That's because it's a figure on the thing. But the vector U has got 3 coordinates. It's got X, it's got Y coordinate, and it's got the Z coordinate. You understand?
Still confusing.
Okay, the vector U here has just been represented as U, but if you write it explicitly, it's going to be written xe plus yg plus zk. It's a 3-dimensional vector still. It's just looking like 2-dimensional because on the paper it's hard to represent it as 3-dimensional. And one thing you should note is that this is just an example here. So it might not contain all the vectors because it's just an example. Because I'm sure you're looking at the E and they're saying, oh, okay, we're no longer dealing with the Z. But no, it's just an example. That's a special case.
So the X1, the X2, and the X3, where are they coming from?
Ah, okay, x1, x2, and x3. Those are the three coordinates. So x1 is the x coordinate, x2 is the y coordinate, and x3 is the z coordinate.
Okay.
You understand?
Yes.
It's just notation here. In this case, it's just notation. No matter what you should look at here, you've seen there's three sums here. We're adding 3 times. That means there's 3 coordinates. But they've used x1, x2, and x3 to just show you that this is a vector. Like maybe this vector is noted by x and this vector is noted by y. Not because we are just dealing with the x and the y coordinates. It's still a 3-dimensional vector because it has 3 dimensions, x1, x2, and x3.
Okay,
and y1, y2, and y3. That's much better.
Yes, sir.
Okay, there's 2 guys asking about, actually 3 asking about the projection. The projection is just the application of the produit scalar when we can apply it. So you are calculating the produit scalar of U and E, 2 vectors, U and E. So, excuse me. And U and E have a vector alpha, not a vector, they have an angle alpha between them. Okay, so from the formula that we looked at for the produit scalar, U scalar E is equal to module de U fois module de E fois cosinus alpha. That's the formula there. Now we have the graphic representation here. We have U like that. This is a vector U going this way. And we have the vector E like that. So now U scalar E. What's U scalar E? For you to find U scalar E, what you do is you will go to the extremity, the last point at the head of U there. And then you will draw a line, you will project a line from U, a line that's going to cut across the other angle in the expression for the produit scalar. Not the other angle, the other vector. I don't know why I keep on confusing the vector U and, the word vector and angle. The other vector, which is E. So from the extremity of U, you draw a line down to U, down to E here. And this line is supposed to be at 90 degrees to this E. This E here. The line is supposed to be at 90 degrees to it. So when you project a line from E, from the extremity of E down to E, the produit scalar is going to be the distance from the origin where the 2 vectors are meeting or starting from up to that line that you've projected here on E. Okay, so if I project a line from U down to E, so starting from here where I've made this line E, going all the way straight down here, straight to the origin, this is going to be my produit scalar. This distance here, it's even been shown with the 2 arrows like that, That's the produit scalar. There's an application we'll look at tomorrow when we do the produit mixed. You'll see it, but that's the application of the produit scalar. This is what is calculated when we're calculating the produit scalar. It is after we project a line from one vector, which is U, from the extremity, down to the other vector, meeting it at 90 degrees, then the distance from that point of meeting all the way up to the origin where the vectors are starting. Now that's U scalar E. That's what it represents, this part here. That's U scalar E. Is it clear for John Banda, Tembo Mike, and Tambafe? Is it clear? Parfait, John Banda. Okay, awesome. Tembo Mike, is clear? And Tambafe, is it clear for you guys? I'll just call you boss. Sure, no problem. Okay. I guess we've come to the end of our lesson today. It's past 17 already. Tomorrow we shall pick up from where we've left them, the produit vectoriel, product vectorial. You guys can go through it and the differentiation. Then we can also try and do these questions down here. If you want, you can do the questions, you can go through them, and you can compare the answers, the beta even, but we'll continue from there tomorrow. Alors, on se verra demain, Inch'Allah, à midi. Yeah, I think mechanics is at 12 tomorrow, so we shall continue the introduction tomorrow. Thank you very much, Teddy. I'm glad you guys have enjoyed the lesson. It's bye-bye from me, and I wish you a good day.
Merci beaucoup.
Yeah, je vous en prie. Thank you very much, Renzo. I'm going to end the meeting now. Mike, you can call, as you said.